class, we did some kind of complicated calculations about lift, how much lift is being generated by an aircraft. And I pointed out the essentials of making that calculation. We have to consider this formula, which seemed pretty complex. We broke it down. The lift being generated is this thing called the coefficient of lift, which is something that's the manufacturers come up with based on wind tunnel tests and other tests with their airframes. And I put here a sample chart that shows you how you get the CL. It's simplified, and again, I just made it for this example. It's not necessarily tied to any specific aircraft. Take the angle of attack in degrees, and this is the CL number that you will get based on this curve. So you look where the curve intersects your angle of attack, cross-reference it, and that's where you get the CL number. So on this chart, I'm going to use our example of 5-degree angle of attack, so the CL will be 1. I just use 1 because it'll be simple to do that. You also have to take into account the altitude, so the air density at different altitudes. And I gave you a chart that showed for every 1,000 meters what the air density is. We're going to do an example of 3,000 meters, which on your chart was 0.91 kilograms per cubic meter. You also need the velocity in meters per second, not in kilometers per hour. If you have kilometers per hour, you have to convert it to meters per second. Then take that number and we square that. Take that whole thing divided by 2, then multiply by the wing area measured in square meters. So I'll run through an example as a means of demonstrating. How much lift is generated by a Sopwith Camel flying at 150 kilometers per hour at 3,000 meters altitude with an angle of attack of 5 degrees. So, with the angle of attack of 5 degrees, on my chart, cross-reference that with this line, gives me CL of 1. So I use 1 for my CL, my coefficient of lift. Okay. 3,000 meters altitude, again on that chart that I gave you, air density is 0.91 kilograms per cubic meter. 0.91 kilograms per cubic meter. 150 kilometers an hour, had to convert that, so multiplied kilometers per hour by hours per second and meters per kilometer, come up with 41.7 meters per second. That's the number we will use. 41.7 meters per second, and this whole value gets squared. Multiplied by the wing area, the Sopwith Camel, again on the charts I gave you, the Sopwith Camel, its wing area is 21.5 square meters. Now, take that, multiply it all out. When I square that, remember order of operations, you have to do the square operation first. 41.7 squared is 1,738.89 meters squared over seconds squared. When I multiply this all through, I'll end up getting 17,010.69 kilogram meters per second squared. When you look at all the units, you'll see that that resolves itself. That is something called a Newton. We don't want to measure it in newtons because we tend to think of things in kilograms. If you divide that by 9.8, we'll get how many kilograms of lift we're generating. So take that answer, divide it by 9.8, you get 1,735.8 kilograms. So it's generating lift to carry 1,735.8 kilograms. If the plane weighs more than that, it'll be descending. If it weighs less than that, it'll be climbing. Hopefully, all this stuff will be useful to you in your future tests.